Hello and welcome to another math lesson. We are on section 10.3. Hello? Down here. Down here. Got it. As I was saying, we are on section 10.3. So let's get started. So we've been doing logs and exponential equations. So 10.3 is more solving logarithmic equations. So we've got our real world example. Turns out that earthquakes can be solved using logarithmic equations as well. So you can figure out the amount of energy released during a 1 month period during a fall of 2008. So 5 medium-sized earthquakes were recorded off the coast of Oregon. So Richter scale right here and the dates. So some mathematical questions, is there a relation between the earthquake and what is felt and where it's measured, between distance, all things like that. What's the equation, maybe? And it turns out, so yes, there is an equation. And you can use that to figure out not only if an earthquake happens here, how much energy will hit, but the reverse, when you feel an earthquake over here, how far away did that earthquake come from? And then you can use some other measurements to figure out what direction it came from, and you can pinpoint the location of the earthquake. So there's a lot of different ways that you can use logarithms. So let's keep going. So we're doing a little bit more of the same kind of stuff. So we're going to start with solve a logarithmic equation graphically. But of course, we're making our equations a little bit more complicated using log base 2. You've got a little bit more complicated equations here. So we can still solve it graphically. We just have to figure out how to put this into our calculator. So again, some of you have these super fancy calculators that won't be a problem at all. But for now, until maybe the super fancy calculators become, super common, you need to know how to do this on a regular scientific calculator. So first, let's kind of figure out some characteristics of this. The expression is undefined when x, and we've got a -1 here. So it's undefined when it hits equal, but also anything less than that. And you'll see that on the graph, so it's going to be less than or equal to. So the graph has an asymptote, a horizontal asymptote, at x equals -1. And so I knew that because our graph shifted 1 that way, 1 to the left. What? Oh, I'm sorry, I meant vertical. So x equals goes up and down. I was thinking that in my head, but. So it says choose the values of x that produce integer values of log base 2 of x plus 1. So this is a good skill to be able to do, just in case you don't have a graphing calculator that can handle this. You can just come up with integers and plot those on a graph by hand, since whole numbers are easier than decimals. So this is going to be a whole number. I would say, remember the definition of log is, where's my pencil? So we could rewrite this like, come on. 2 to the power of blank is equal to x plus 2, or x plus 1. And so anytime we could express this as a factor of 2, then we should be in good shape. So we've got 0. If we were to make this y equals 0. So that works only because anything raised to the 0th power equals 1. But then other than that, we've got our 1. This would equal 2, 3, 9. Oh no, and 15. So these are all, so 16, if we do x plus 1, could be rewritten as a factor of 2. If we plug 3, 3 plus 1 is 4, could be written as a factor of 2. So that's where I'm getting these numbers from. And of course, I got carried away with the 9, but whatever. So here's our graph of our function. And so they used the integers that we just found to make that graph. And so we know that it has a vertical asymptote here at -1, and we can make that graph. So the right side of the graph given equation is 3.5. Use the graph to locate the point on the graph where y is approximately 3.5. So this is 3.5. I'm going to say that's either 4.5 or 5. I'm going to try 4.5. Out to the point to the nearest integer. And I'm going to try 5. Try a different strategy. So I did 5, then I'm going to try 4. What? Find 3.5 on the vertical axis. So here's 3. Oh, I was down here. Zoom in. I was down here. I should have been up here. That was my fault. Okay, let's go 10. 10 seems like a good try here. Oh, look at that. When you use the right stuff, you get the right answers. So if you did want to use your calculator and you didn't have a log base 2 button, how could you do it? So you could use the change of base property. So remember that was, if we were going to change this to a log base 10, it would be common log of 2, no, that's wrong. Common log of x plus 1 over common log of 2. And so then you could graph that and then find where that equals 3.5. To be completely honest, that's probably what you're going to do more likely out in the real world, but got to kind of have a context for it all, right? So more solving logarithmic equations graphically. So it says solve the equation 5 natural log of x plus 2 equals 9 using a graphing calculator. So this is one of those situations where natural log is on most calculators, and we can solve this using that calculator. So what two functions will be graphed together on the graphing calculator? So we're going to have, so our y equals 5 natural log x plus 2. And then when is that going to equal 9? So we're going to do a y equals 9. What did I do wrong? Oh, duh. So that has a 9 in there. That was my bad. I love these things. Not this one. Take a deep breath and try again. Reading, it's a thing. So y equals 5 natural log of x plus 2. So what will the graphs of the two functions look like? The graph of this will be a logarithmic curve, and it will be blank to the right from its asymptote. So it will be increasing, going up, because it's greater than 1 inside of the natural log. At its asymptote at x equals -2. And the graph of y equals not y is a horizontal line. Yay. All right, so finally we can use a graphic calculator. We can figure this stuff out, right? So let's do it. So we're going to go to our y equals. Here are our other stuff. So is it 5 natural log x plus 2? So 5 times natural log x plus 2. Notice how you don't actually have to do a multiple sign right there. The calculator assumes as much. And then we have y equals 9. Bam. So I didn't mess with the window because I knew that I felt like we were going to see it no matter what. So here's where we can use our calculate button. Intersect. That's our first curve. That's our second curve. The x-intercept at y equals 9 is 4.049. I'm going to write that on the screen. 4.0496 for now. The point of intersection occurs at approximately the nearest hundredth if necessary. So the x was 4.05 and what y equals 9? No. Boop. Yay. The nearest hundredth, what is the solution of the equation? The solution of the equation occurs when x equals 4.05. So when those two lines intersect, whatever, is where our answer is. Solve a logarithmic equation algebraically. Yes! It's the best way. So in addition to solving logarithmic equations graphically, you can also solve them algebraically. So this whole section kind of goes very similar to what we did last section with exponents. This time we're using logarithms. So similarly, let's see, last section or something like that, we said if you had, some constant raised to the power of x equals that same constant raised to a different power, you can then say that x is equal to y. Well, in the same way with a logarithm, you can do that. For all real numbers b, I'm sure that's some Greek symbol. I think it's supposed to be, I don't know what that is. But anyway, for all numbers b, x and y, log of b of x equals log of b of y if and only if x equals y. So it's the same thing, but in this case, you have to make sure that your bases match up. So it has to be log base blank, the same thing. So let's try it out. So we've got solve log base 6 of 3x plus 7 equals log base 6 of 5x minus 1. So we check our logs. They are the same. So now we can just go straight into 3x plus 7 equals 5x minus 1. So this is something that I hope that you can solve by this point. You put the x's on one side, the y's on the other. Let's put the x's on the right. So then we will have 2x equals 8. So x equals 4. Too easy. If you don't believe me, they did the same thing. So of course there's going to be questions. What property justifies the first step? Property of equality for logarithmic equations. Property of equality for exponential equations, what we learned last lesson. What property justifies the second step? Basic algebra. let's see, what do we do? Property, addition, property of equality, or subtraction, but they're probably want subtraction, let's be honest. So what is the result when you check the solution in the original equation? Ooh, let's do that. So we got, what, x equals 4? So we can use our calculators, and you can plug in y equals 4. I'm sorry, x equals 4. So we got, what, 3. So 12 plus 7 is going to be log base 6 of 19. And then we can, the other side, log base 6. So 5, we said 4, so that'd be 19. And look, they're the same. Done. Too easy. Solving logarithmic equations algebraically, but this one is cool. Look at that, baby. How are we going to solve that? Let's get some white space. So solve common log of 8x plus common log of 20 plus x equals 3. So first things first, we can combine these two things based on our properties of logs. So because they're adding together, because they are the same base, they are both common logs, we can say that that is the same as or equal to log base 10 of 8x times 20 plus x equals 3. Okay, so now we can simplify all of that, basic algebra. So we'll put our log here just for scientific accuracy. So we've got 8x plus, our 8x times 20 is going to be, what, 160x plus 8x squared equals 3. So just like a normal factoring problem, we can factor some stuff out of there. So actually, what they did is kind of clever. I like it. So I'm looking right here. And I was like, oh, what did they do? Oh, so the definition of log, right? So log base 10. So log base 10, and then we put the 3 right there, is equal to 160x plus 8x squared. So at this point, this is just a regular algebra problem, right? Something we've done before. So, I'm going to rewrite it. I'm going to bring this over to the other side, and then I'm just going to write it in a way that we're kind of more used to. So we're going to have 8x squared plus 160x minus 1,000 equals 0. So from here, can we factor that 8 out? Yeah, so we're going to pull that 8 out, see if this thing is factorable normally. 8x squared plus, I think that's 20, right? $20x minus 125 equals 0. So if I were to factor this normally, I need to find two factors of 125 that 1 added, 1 subtracted equals 20. So 125 divided by 5. Ha! Yes. I just guessed there. So 125's, one of its factors is 25 and 5. So if we add the 25, subtract the 5, we should be in good shape. So now we've got 8 times x plus 25, x minus 5 equals 0. So now our x equals negative 25 or 5. X equals negative 25 or x equals 5. Right here. See, that is some good algebra right there. So let's see, what property justifies the first step? That would be the property, let's see, we added, which is a, no, quotient power. Is it that one? Take a deep breath. Product is when you multiply things together. Or not. Maybe I'm wrong. Oh, because it's multiply. I was looking for addition. My bad. So how does the second step follow from the line above? The definition of logarithm. And what happens when you check the solution. I'm going to let you do that. You're going to probably get the same number on both sides. You should be able to plug the log base, or the common log base 10 into the calculator. Or you should be able to do it by hand. Obviously, we need a real-world problem modeled by logarithmic equations. So when solving real-world problems, algebraically, always check your solution makes sense in the context of the situation. For example, distance in the real world cannot be negative, so we've talked about a lot of this stuff. So let's try one. Often, the real world restricts values to positive numbers. For example, if a box minimum, okay, yes, we know. Got it. So Pollux, that star right there, the head of Gemini, the Gemini twins, Castor and Pollux. Pollux, apparent magnitude of 1.16, absolute magnitude of 1.09. The brightness of the star, as measured from Earth, is its apparent magnitude, m. The absolute magnitude, capital M, is the brightness of a star from a standard distance of 10 parsecs. These measures are related by the formula little m minus big M equals 5 log d over 10, where d is the distance of the star from the Earth measured in parsecs. How far is Pollux from Earth? So this is like, I love astronomers because they can figure out the most amount of information from the least amount of data. Like, oh, based on the brightness of the star, we can figure out its distance. That's crazy! But it's cool. So let's figure this out. So we've got our equation where little m is the apparent magnitude. So that's right there. So our little m is going to be 1.16 minus 1.09 equals 5 log base 10 of d. Oh, I messed that up. I got to rewrite that. Of d over 10. So now we just got to solve that algebraically, right? So we've got 1.16 minus 1.9. So we're going to have 0.07, right? Equals all of this stuff. Not a huge, well, actually, no, never mind. Yeah, let's get rid of this 5. So we can divide both sides by 5. So now we've got, I'm busting out the calculator for this. 0.07 divided by 5. 0.014 is equal to log of d over 10. So now, based on our definition of a log, so that is log base 10. So we've got, wait, is that what we want to do? Log base 10, yeah. So that's going to be log base 10, got it from right there, raised to the power of this guy, 0.014, is equal to d over 10. Okay, so we're going to times both sides by 10. Don't need a calculator for this because 10 raised to an exponent times 10, you should remember from your power rules, that's just going to be 10 raised to the power of 1.014. Now that is something you can finally put into your calculator. 10 to the power of 1.014 is 10.33 equals D. Which is what they got. So that means that Pollux is about 10 parsecs from Earth. Also for my Star Wars fans, that's why making the Kessel Run in 10 parsecs is not a real thing. So then, let's see here, how does the third step, that, follow from the line above? Where's this one? From the line above. Division property of equality. We'll go for that. What justifies the fourth step? Definition of log. I'm getting good at some of these questions. How can you use a graphic calculator to verify the answer? Graph, y equals that, and y equals, what was it, 1 point, yeah, 0.07, not 1.0, 0.07. And the solution should match the x value. If 10 parsecs are equivalent to approximately 32.6 light years, how would you calculate this between Pollux and Earth in light years? So we know that 10.3 parsecs, I'm sorry, that Pollux is about 10.3 parsecs away from Earth, about 10 parsecs is equivalent to 32. I mean, so you just can set up a proportion, which we're going to do right here. So is it reasonable to say that Pollux is about 30 years? So I'm going to say yes, 30 light years. Sorry. Rounding to the nearest tenth. If you just plug this, all this into your calculator, you get 33.6. So they just set up a proportion essentially. Should have labeled their units better. That should be parsecs. But I spelled it wrong, so whatever.